Oh, there we go. I only did that a couple hundred times last year. All right, so for this Math League meeting, I'm not sure if it's really a meeting, but I just thought I would take this opportunity to show you guys some techniques and tricks as I look at event A from the first meet. There's some stuff that's pretty straightforward, and then there's some other stuff that's a little bit off the wall, stuff that it's easy for me to show you how to do it in such a way that you might have never thought to do it. So I'm going to get my document camera fired up here so I can write on paper and you can see. So we'll see how this goes. So I want to take a look at what I'm going to call nested expressions. Oh, and I need to record. Dang it.
You're still recording.
It is recording. Okay. So when I say nested expressions, these are things that show up every once in a while on event A. And if I go through them now, I hope that you'll have a shot at it. If I don't go through it, you're going to have no shot, no chance to get it. I shouldn't say that. You could take a guess and come up with a pretty good answer, depending on what it looks like. And I was messing around with this one. I should have been paying closer attention in some of our professional development today, but I found a good one that looks like this. Suppose x is equal to 2 plus the square root of 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 2 plus ... And it goes on like that forever. How in the world are we supposed to do this? Now, when this appeared in some past years, it would happen on an event where a calculator was allowed and students could basically just do it a few times and start to kind of notice what it looked like. But this year, one of the things that I learned yesterday is that all of the individual events are going to be non-calculator. And so if something like this shows up, what are we supposed to do? Now, before I do it, I'm going to ask the 12 people that are here, does anyone know how to evaluate an expression like this? Don't see anyone unmuting themselves. So it goes like this. And this is one of those things when I show you, I hope you're going to be like, oh, I guess that makes sense. But if I don't show you this, you'd have no idea how to even start. Well, I'm going to say x is equal to 2 plus the square root of x. What? Because x is defined as 2 plus the square root of 2 plus the square root of 2 plus the square root of 2 plus et cetera, et cetera, et cetera. So when I replace, let's see, if I could, I guess I'll just take that part of it. This part of it is x. It's this repeating version of 2 plus the square root of 2 plus the square root of 2 plus the square root. So whatever that is x. And so I can take that and plug it into this expression, replacing, well, what it is. And all of a sudden, I've gone from this crazy, bizarre, infinitely defined expression to, well, this. And this is just something that you could have solved in Algebra 2. I'm going to subtract 2 from both sides of this equation and get x minus 2 equals the square root of x. And then I'm going to solve that by squaring both sides of the equation. So I'll square x minus 2. Something I learned from my honors functions and trig classes on Friday is that foiling is something that some of us have forgotten how to do. X minus 2 squared is x minus 2 times x minus 2. The square root of x squared is x. I guess I'm ignoring negative values, probably because all of this stuff would have to result in a positive value. So I'm just going to say that the square root of x squared is a positive x. And then I'll FOIL that out. X times x minus 2 times x minus another 2 times x minus 2 times negative 2, so plus 4. And so there we go. I've got a quadratic equation. If you have taken Algebra 2 or beyond, you've solved quadratic equations. I'm going to solve this by moving everything to one side of the equation. Let's see, minus 2x minus another x. I've got minus 5x. Equals 0. And there have certainly been questions like this in Math League where factoring is not possible. You have to do the quadratic formula, and it might ask you for the positive answer or something like that. But in this case, this is factorable. Can anybody think of two numbers whose product is 4 and whose sum is negative 5? Andrew says negative 4 and negative 1. So if I had x minus 4 and x minus 1, so x squared minus 4x minus 1x brings us to minus 5x, and negative 4 times negative 1 gives us 4. So it looks good. If x minus 4 is equal to 0, that means x is equal to 4. If x minus 1 is equal to 0, x is equal to 1. And here's another case where instead of getting two numbers from the quadratic formula, I'm getting two numbers, but only one of them is going to make sense. If x is 2 plus a whole bunch of positive stuff, I'm going to throw out that positive 1 and say that the value of x is 4. So there we go. That is one version of nested expressions. The other one, the other version that I saw show up, I'm looking at the practice examples that I gave you guys on 2018-19 event A. There's problem number 4 that is, well, I guess I'll write this out. It's kind of similar, but it's also a little bit different. We've got x equals, and it's 1 divided by 1 plus 1 divided by, this one zigs a little bit, 2 plus 1 divided by 1 plus 1 divided by 2 plus 1 divided by da, 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 da. And so this one has a little bit more going on. We have to go a little bit deeper into the fraction before it starts repeating the exact same thing over and over again. But if I take this chunk of it, that's the same thing as what x was. 1 divided by 1 plus 1 over 2 plus 1 over, and then it's just repeating the exact same thing. So I don't want to go through this one, especially because you also have the answer key in the PDF document that I gave you guys, but I would treat this as 1 over 1 plus 1 over 2 plus, and that's where everything else is repeated after that point. So this is definitely a little more complicated equation. You'd have to do some fraction manipulation, but I'll let you guys take a look at that one on your own. I've seen this with fractions, I've seen this with radicals, and I've seen both examples that happens once every couple of years in Math League. But there we go. Any questions or comments about that? And you're all just like, Crowett, you're lucky I'm here on a Monday when I don't even have to go to school. Stop bugging me to participate. We all good? I see some smiles, some somewhat smirks. Good to see. All right. The other thing I want to take a look at is different number bases. And this one is a little bit more consistently on event A, but the context in which it shows up is a little bit, there's a little bit more variety to it. I'm just going to read off some that I saw. I guess I can just show you. This one is 2017-18, number 3. What is the base B for which 68 base B is 25% larger than 53 base B? And then they clarify and say that 25% larger is back to our comfortable base 10. If you have no idea about different number bases, sorry, but you got no shot on this problem. Same thing with, this is number 2 on 2016-2017. Find the base 9 number that is equivalent to 245 base 6. And some of you are looking at that. If you've never seen different number bases before, you're looking at that saying, This is a foreign language. What does base 9 number mean? What is that little subscript 6? And so I thought I'd give you, in the little time that I want to take today, if nothing else, I'll give you a little bit of an introduction, and then if you wanted to go and maybe hop on YouTube and look for different number bases or something like that, you'll be able to do that. And I struggle because I know that we're a little bit all over the board. I know for a fact that some of you have seen stuff like this, and I also know with fair certainty that some of you have no idea about that number-based systems exist. And so I think the way I'm going to do this is I'm going to say our numbering system is built upon the fact that we have 10 digits. So like literally human beings have 10 digits. And when we start counting things, we count on our digits. There's 1, 2, 3, 4, 5 sheep out in my herd. And I've got 6, 7, 8 apples that I'm putting in an apple pie. And if I have more than 10 of something, I run out of digits. And so I have to keep track of, well, when you guys were learning about number bases, you learned about if I have a number like 7, and that's it, you know that that's just 7. But if I have 87, you know that that's not 15. It's not 8 plus 7. It's 8 tens and 7 ones. And if I've got something like 5,187, again, this isn't 5, comma 1, comma 8, comma 7. This is 7 ones, 8 tens, 1 100, and 5 1000s. 5,100, 8 tens, and 7 at the end. And so when we look at different numbering systems, it's going to look very similar. This could be base 10 that we're used to, or this could be base 12 that we're not very used to. This could be base 60, which we're certainly not used to. And I see that Henry is here with us today. This is something that Henry and I were talking about during class sometime last week. So to introduce this, I'm going to start by imagining what if instead of the 10 digits that we have, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are our 10 digits. And so I want you to think about if we were going to write down numbers with a number system where we only had 4 digits. So what if we had, I'll just call this base 4. So our only digits, the only digits we're allowed to use are 0, 1, 2, and 3. Those are our 4 digits. We're living on a planet where everyone walks around and this is what their hands look like. They only have 2 fingers on each hand, so they literally have 4 digits. And so as we start numbering, 0 is 0, followed by 1, followed by 2, followed by 3, and now I'm stuck. I can't count any further than that because I've used up all of my digits. So the next number in line, well, I'm going to have to go, instead of to the tens place, because we've got a base 10 numbering system, I'm going to go to the fours place and say that I've got 1 4 and 0 ones. I've got 0 ones, 1 1, 2 ones, 3 ones, and then I'm out of digits. So now I've got 1 4 and 0 ones. And then I've got 1 4 and 1 1, so that's 5. What we know as 5. Got 1 4 and 2 ones. That's what we would call 6. 1 4 and 3 ones. There's 7. And I'm out of digits. I can't go any further than that because I'm only allowed to use 0, 1, 2, and 3. So I've got to keep track of that. I've got now 2 4s and 0 ones. So 4, 5, 6, 7, here's 8. 2 ones is 8. And I'll go just a little bit further. I'll be able to get to a 3-digit number fairly quickly. Whoops, 22. What looks like 22 to us is really, let's see, this would be 2 4s and 2 1s, so that is what 10 looks like. There would be 11, and then by the time we get to 12, we've got 3 4s and 0 1s. 3 4s and a 1, 3 4s and 2 1s, 3 4s and 3 1s, and now we are as big. This is like our 99. When we get to 99, if you're driving in a car and you get to 99, that's when the odometer flips over because we're at the end of both of those digits. And so here's our first 3-digit number in base 4, where this is 1s. I've got no 1s, I've got no 4s, but I've got 1 what? What does this place represent? Someone who understands what I'm doing, let me know. What does this place represent? This is 1 what? Oh, and Andrew's typing it. Yeah, 16. I've got 116 and no 1s, or sorry, no 4s and no 1s. And so this is the point at which I'm going to think about this. As we're looking at these digits, this is 0 1s. That 0 means that I've got 0 4s, and that 1 means that I've got 1 16. And maybe you're looking at this and thinking, well, that's a weird way to keep track of numbers, but that's how we keep track of numbers in our numbering system. We just don't think of it as 1s, 4s, and 16s. We think of it as 1s, 10s, hundreds, and thousands. And if you think about 1, 4, and 16 and the relationship 1 to 4 to 16, we're multiplying by 4 to go from one to the next. Here we've got 1s, 10s, hundreds, thousands. Each place value is 10 times bigger than what the place value was before it. Just like here, each place value is 4 times bigger than the one before it. So when I see a number like 5,187, if this is base 10, by the way, how's my legibility? Thumbs up, thumbs down? Doing okay? At least the 4 people with their video on, and 1 person who must be lying in bed. Or maybe Henry, the camera is pointed above your head, which I didn't know was physically possible, but okay, there we go. There we go. If this is base 10, if I'm looking at this number, 5,187, if this is base 10, I'm thinking of that as 5 thousands, but I'm going to call those 10 to the thirds. And that 1 doesn't represent just 1. That 1 is really 1 100ths, but I'm going to call that 10 to the second. That 8 is 8 tens, or 10 to the first. And that 7 is 7. And I know it's just 7, but I'm going to call it 7 times 10 to the 0 power, which is 1. And so our numbering system is dealing with these powers. We just never write it out. We know it's something that you learn in first grade, second grade, when you start learning about place values. We're just not used to seeing it in this form. And so if I told you, oh, by the way, this actually wasn't a base 10 number, this 5187, if this is actually in something called base 16, sorry, I need to keep my paper in frame here. If I said that this number, 5,187 in base 16, what number does that represent? I'd have to think of it as 5 times 16 to the third power, plus 1 times 16 squared, plus 8 times 16 to the first, plus 7 times 16 to the 0. And so I'm actually going to plug this in my calculator and see what it is, just out of my own curiosity. Let's see, so 16 to the third times 5 plus 16 squared. 16 squared is, well, plus 8 times 16 plus 7. So this 5,187 base 16 is the same as 20,871 in our base 10. And that in a very small, I don't know what that was, but that felt like about 10 minutes that I was talking about that. That's a very crammed nutshell that says we can have this number, and in different number bases, it can have very different values. I mean, look at that. It's almost 4 times bigger, which, I don't know, that's kind of interesting, I think. Any questions? I would like to do one of the Math League problems just to kind of show you how it works and how we could actually do one of these in the time that we got left. All right, well then let's take a look at, and I've just got the one that I've got up in front of me right now. So what is the base B for which 68 base B is 25% larger than 53 base B? And so if I was doing this problem, I would say, let's see, 68 base B, whatever that is 25% larger. So I'm going to say is 1.25 times, what was it, 53 base B. Now, if we're in decimal notation, this doesn't work. If this is literally 53 as we know and love it, and if this is 68 as we are familiar with it, 53 times 1.25 does not equal 68. So the answer is not 10. This is not a base 10 number. And so the way I would approach something like this is I would do kind of similar to what I was doing with the previous one. I was a little bit scared because when I was trying to figure out how to do this problem, I think if this is a 3-digit number, this problem gets significantly more difficult. But it turns out I'm going to represent these numbers similar to how I was representing this 5,187 in base 10 versus base 16. I've got the ones digit times 1 plus the, well, 16th digit or 10th digit or whatever it represents, but I've got that, well, in this case, 8 times. In this case, I've got it 6 times. So I'm going to say that this is not just 6, but this is 6 times whatever my base is to the first power plus 8 times whatever my base is to the 0 power. And again, this starts to look scary. If that gets to be second power, third power, this gets a little bit more scary. But as it is, we're going to be all right. 1.25, and here I go. I thought I was going to be done by 4, but I'm going to go just a little bit over today. That's okay. 53 in base B is 5 times B to the first power. I've got 5 B's, whatever they are. I've got 3 1s, which at least for right now I'll write as B to the 0, but I could ignore that and just say that that's 3 times 1. In fact, I'm going to go ahead and do that. I've got 6 times B plus 8 times 1 equals, and at this point I realize that I'm going to have to do some algebra, and if I'm not allowed to use a calculator, I think it's going to be easier if I treat that 1.25, whoops, I should use some parentheses there. I'm going to call that 5/4, and that's going to make the algebra a little bit easier. And here I've got 5B plus 3. And I've got myself an algebra problem. 6B plus 8. I'll distribute that 5/4 and call this 25/4 B plus 15/4. I'm going to multiply both sides of the equation by 4 to get rid of my fraction. Not that I'm fraction phobic, but I know a lot of my students are. That'll give me 24B plus 32 and 25B plus 15. And now this looks like an algebra 1 problem. I'll subtract 24B from both sides and get 1B. And then I'll subtract 15 from both sides. And 32 minus 15 is 17, and I just got my answer. Apparently these numbers, the 68 base B and 53 base B, apparently the number base is base 17. So this is not just 68, this is 6 17s plus 8, and this is 5 17s plus 3. And I'm at 4 o'clock here, so I will wrap this up, but I will say that as abstract and weird as this may seem, number bases have their place in a lot of really cool mathematics, including, well, computers. If you've heard of binary notation, the language of computers. The video that you're watching right now to your computer processor is just a very long string of ones and zeros. And Sylvia and I feel like, Sylvia, when it comes time, you and I are going to have to do a binary demonstration for our 7th hour class. We'll have a traveling roadshow of the binary father-daughter duo. But I think that's probably a good place for us to stop. We'll meet in person again next week. We'll go through a couple other things from Event A and Event B. Hopefully you've had a chance to try out some of those. If you haven't taken a look at Event B, please look at Event B before we see each other again next time, and I can show you some of the tricks of the trade for that one. Any questions from the group? All right, well, there's your two-headed Math League advisor back. Thank you all for being here. Thank you for making it worth my time to organize this. And one last thumbs up, thumbs down. Was this worth your time today on this lovely Monday? You are all making me very happy. Even though, Henry, your video is upside down, so that looks like a thumbs down, but I'm able to transpose. Okay, there we go. That's much better. All right. Awesome, guys. Have a great Monday. I will see most of you tomorrow and the rest of you next week. Bye-bye. You're welcome, Noah.